Okay, today we're starting our Chapter 17 lecture on aqueous ionic equilibria, and this is heavily based on our Chapter 16 weak acid, weak base reactions in ice boxes. So if you aren't very familiar with that yet, review those notes and then continue on with this lecture. Okay, so a quick topic on the common ion effect. So the common ion effect, this talks about adding a common ion to an aqueous or weak acid reaction. So this is our weak acid, acetic acid. It's a carboxylic acid. And it reacts with water to produce hydronium and the conjugate base, acetate. And you could imagine that if we were to add more acetate or more of this ion to our beaker, based on Le Chatelier's principle, our reaction would shift to the left. And if the reaction shifts to the left, I know that so the reaction shifts to the left when I add more acetate. And if I'm adding more acetate, the reaction shifts left, and then I can imagine my hydronium, if it's shifting left, goes down, and if my hydronium molarity goes down, the solution has less acid in it, it's less acidic, higher pH. So what we're going to see, we're going to, throughout this chapter, look at solutions that contain both the weak acid and its conjugate base. And we looked at this in our pre-lab workshop on Thursday as well, where we had a solution containing sodium carbonate and sodium bicarbonate. So again, common ion effect, you add a common ion to that reaction. Based on Le Chatelier's principle, the reaction shifts left, hydronium molarity decreases, the solution is less acidic. So now let's look at this, our first practice exercise. Calculate the pH of a solution containing 0.085 molar nitrous acid. Again, a weak acid. I know it's weak because it's not one of the 6 strong acids I memorized, and I'm given a Ka. And it also contains a 0.10 molar potassium nitrate. So nomenclature, again, very important. I gave you the chemical formula, KNO2, so we have a weak acid and the conjugate base. Potassium is just a counter ion to keep this solution charge neutral. So let's go ahead and look at how we're going to solve this problem. Okay, so this is essentially looking at our weak acid hydrolysis problem from last chapter, except now, instead of just the weak acid, we also have the conjugate base. We're going to calculate it the same way. So the steps for calculating the weak acid pH problem, write the hydrolysis reaction in our Ka expression. So hydrolysis reaction, you're reacting the weak acid with water. 2, ICE. And then 3, think, how do I solve for X? So, right in a reaction, I have my nitric acid reacting with water in equilibrium with hydronium and nitrate, the conjugate base. I left out the potassium because that's my spectator ion. It doesn't affect my pH or the equilibrium. Remember, K plus has no effect on pH. So I have my weak acid equilibria, Ka products over reactants, leaving out water. ICEQ. Initially, I have nitric acid as a 0.085 molar solution and potassium nitrate 0.10 molar. Nothing is mentioned for hydronium to begin with, so that means it's a 0 initially. Our change, just as last chapter, minus X for the reactants, plus X for the products. At equilibrium, I add up the columns. So 0.085 minus X, 0.10 minus, or 0.10 molar plus X. Now we're on to step 3. How do I solve for X? Well, I'm given the Ka. Now Ka equals 4.5 times 10 to the negative 4th, and that equals just products of a reactant. So my hydronium is X, nitrate 0.1 plus X, nitric acid 0.085 minus X. One equation, one unknown. We're going to assume that X is much smaller than the number that you're adding it to or subtracting it from. So rewriting that, again, instead of X, we're going to assume that 0, and the purpose of this is just to avoid using the quadratic formula. And I end up with my Ka equals X times 0.1 divided by 0.085. So solving for X, I multiply both sides by 0.085, divide by 0.1. I got 3.8 times 10 to the negative 4th. So that is quite small. We want to go ahead and do our check. Is X really small compared to the number it was subtracted from? So we're comparing X to either 0.1 or 0.085. You just compare it to the smaller number, because if X is smaller than 0.085, it's definitely smaller than 0.1. So x divided by the 0.085 times 100 gives me, and again, x was our 3.8 times 10 to the negative fourth, over 0.085 times 100, 0.45%. So that means that this is an appropriate approximation, and now we can solve for pH. So, as long as x is 5% or less, we're good to go. Now, pH, remember negative log over hydronium molarity. Remember, X is again our hydronium, H plus, H3O plus, same thing. And I got 3.42. Again, two significant figures in the molarity results in 2 digits past the decimal point. Okay, so moving on, we're now talk about buffers. So notice in this problem, we're looking at a weak acid and its conjugate base. And that's exactly what a buffer is. So a buffer contains equal or similar concentrations of a weak acid and conjugate base. So another example is HF and F minus. And what we're looking at in this animation, we're adding small amount of hydroxide. So let's read this. If a small amount of hydroxide is added to an equal molar, that just means the same number of moles, a solution of HF and NaF, so weak acid, conjugate base, Na is a spectator ion. For example, the HF reacts with the hydroxide to make F minus in water. So what are we looking at here? We have a buffer. We'll talk about buffers for the next couple slides, but right now, a buffer is a solution that contains a weak acid and its conjugate base. In this example, I'm adding some strong base. So we're going to look at calculating the pH of a pure buffer, just a weak acid conjugate base, which we did on this previous slide. We essentially calculated the pH of a buffer. We're also going to look at calculating the pH of a buffer after adding either strong base or strong acid. So, strong base situation, what happens? The strong base reacts with the weak acid to produce more of the conjugate base and water. So, this hydroxide deprotonates the HF, so the hydroxide turns into water, HF turns into F minus. And what's going to happen is we're adding just a small amount of hydroxide. That's always going to be our limiting reactant. So the product that we end up with, we still have a weak acid and conjugate base. Therefore, it's still a buffer. And that means the pH is going to be very similar to the initial pH. So important to remember, strong base reacts with the weak acid to produce the conjugate base in water. We can also look at a buffer adding H plus. H plus reacts with the conjugate base, so acids and bases react to make more HF. So after the addition of a small amount of H plus, we still have a buffer solution. The pH will be very similar. So again, the H plus would just protonate some of the F minus to make more HF. So similarly, if an acid is added, the F minus reacts with it to form HF in water. So it's really important to remember acids and bases react. Acid and base reacts to form the HF. Over here we had our weak acid, strong base reacts to form the F minus in water. So those are two really important reactions for these problems. Okay, so now we're going to look at some buffer calculations. Consider the equilibrium constant expression for the dissociation of a generic acid HA. So we're going to see if we have a buffer, there's a shortcut, and we do not need to use our icebox. So this is the derivation of our shortcut equation. So if we think about our weak acid reaction, HA and water, to make hydronium and A minus, I know my Ka is products over reactants, right? Ignoring water because it's a liquid. And we're going to just, tiny algebra, pull hydronium out. We'll then take the negative log of both sides. So negative log of Ka equals negative log of hydronium plus negative log of A minus over HA. Because remember, our rules of logs, so we can separate these into two different terms down here. So now we're going to rearrange, or I know an A minus is my conjugate base. HA is the weak acid. So again, HA will always be a weak acid. Negative log of hydronium is indeed a pH. And remember, negative log of a Ka is a pKa. So bringing this all together, we end up with what's called our Henderson-Hasselbalch equation. So Henderson-Hasselbalch equation is the equation we'll use to solve for the pH of a buffer solution. I'll be using the shorthand notation as HH equation. I think it's easier to remember. So when can we use the HH equation? When can we use a buffer? So the pH range, a couple definitions here. pH range is the range of pH values over which a buffer system works effectively. So a buffer is a solution that contains a weak acid and its conjugate base, and it is resistant to pH change, but it's only resistant to pH change in a certain region, and that region is dependent upon the weak acid that you're working with. So it's best to choose an acid with a pKa close to the desired pH. So if you want, let's say, a desired pH of 4.00, you look for a weak acid as a pKa close to 4. So let's look at a practice exercise. 1, so what we did before with just a few minutes ago with the ice box. Remember how I said that's a buffer because we have a weak acid and its conjugate base? Let me flip back real fast just to remind you all of what we were doing. So weak acid, conjugate base, hydrolysis, icebox, solve for X, shortcut, make sure it's small, solve for pH. We got 3.42. We're going to see how now, realizing that a weak acid and conjugate base is a buffer, we can use our HH equation, and it's a much faster problem solving technique, and we'll get the same number. So 3.42 we saw before. So now hopping back to redoing practice exercise 1, this time with the HH equation. Okay, so now that we recognize it's a buffer, we can use our Henderson-Hasselbalch equation. pH equals pKa plus log of base molarity over acid molarity. And that gives us a pH is, remember, pKa is a negative log of the Ka plus log of the base over the acid molarity. And I got for my pKa 3.34, the log of 0.1 over 0.085, I got 0.07058, which results in a pH of 3.42. So again, much faster than hydrolysis, ICE, solve for X, check, and then get your pH. So in order to use the HH equation, you need to recognize the solution that you're looking at as a buffer solution. That's very important. So a buffer, weak acid, and conjugate base. Now let's look at practice exercise 2. Calculate the concentration of sodium benzoate that must be present in a 0.20 molar solution of benzoic acid to produce a pH of 4, and you're given the Ka of benzoic acid. So thinking about this problem, I recognize this is a weak acid. I see that's a carboxylic acid, that's COOH, benzoic acid. And I'm asking for the concentration of sodium benzoate. So this is a weak acid and its conjugate base. I recognize it's a conjugate base. I know sodium is a counter ion. Benzoate, 8 turns into ic acid, right? So that's the polyatomic anion. C6H5COO minus, weak acid conjugate base. So you'll be using your HH equation. So I'd like you to pause the video, use the HH equation to solve for your molarity of base. After you've done that, hit play, and we'll go over this together. Okay, so hopefully you took the time to go over this practice problem on your own, and I'll walk you through it to make sure you got the correct answer. So we're using our HH equation because I've got a weak acid and its conjugate base. This time I'm given the pH of 4. I have a Ka, so I can solve for a pKa using the negative log, plus the log of base, which is what we're trying to solve for, our sodium benzoate, over the acid molarity of 0.20 molar. So working through the algebra, the negative log of the Ka is our pKa, I got 4.20. I'm now going to subtract 4.20 from both sides and then take 10 to cancel out the log. So I get 10 to the 4 minus 4.20 equals the base divided by 0.2. So on your calculator, 10 to the negative 0.2, right, times 0.2 to get my base molarity. And I got 0.13 molar. So this would be the molarity that you would need to mix in with a 0.2 molar sodium or benzoic acid solution that would result in a pH of 4. You can double check that you did the math properly. You plug in 0.13 for the base, use the pKa that we had, you should get 4. You can double check your work. Okay, so I'm going to stop this video here at the end of practice exercise 2, and then I'll pick up with the adding a strong acid or a strong base to the buffer in the next video.